Today we will discuss about the column flanges with the concentrated forces. And in frames with moment connections, the girders that frame into the column flange exert both tensile and compressive concentrated forces, creating a moment couple on the same side of the column. This we can see in the figure. These double concentrated forces can be applied on one side or both sides of the column. In gravity loaded frames, the girders on either side, the forces are tensile at top and compressive at the bottom of each girder. When lateral forces are applied, the forces on opposing sides of the column act in the same direction. We can see some. Here we can see these are the double concentrated load. Here you can see this is going to be tension, it's going to be compression. This gravity load top flange it will be in tension, bottom flange it will make compression at this the portion of the column. And lateral loads, if it is applied here, it will cause one side the tension and other side compression. This kind of lateral loads it will cause. So the tensile forces on the column can lead to failure due to local bending, while compressive forces may cause web failure through buckling or shear in the panel zone, right? So if the required strength surpasses the available strength, transfer stiffness or web doublers or both can be added to address these kind of issues. Alternatively, selecting a heavier column that can offer most cost-effective solution. Also, we can do it. Additionally, columns can fail due to web local yielding or crippling. The topics we can see it in the chapter. Flange local bending, we can see the flange local bending occurs when a tensile force is local bending occurs when a tensile force, not compressive force. You can see when the tensile force is applied to the column flange, especially at the moment connections with girders framing into the one or both sides. We will show the figure also. As shown in this figure, stiffener plates, also known as continuity plates, may be used to strengthen the slender column flanges. These stiffeners typically installed in pairs and welded to the loaded column flange. For a girder framing into only one side, the stiffeners need not extend more than half the depth of the beam. If it is only one side coming, there is no need to extend it. So the forces transferred from the girder flange to the column can be expressed as mr divided by dm plus pr by 2. Here we can see this is the moment mr. Dm is this one. Dm is the distance between the flanges, that is the total depth minus thickness of flange. D is the girder depth. Tf is the girder flange thickness. Pr is the axial force in the girder. So this force is mr divided by dm. Usually the axial force in the girder is small and may be neglected. Otherwise that will become pr divided by 2. pr is the axial force here and here, right? So this half it will be taken because axial force can be taken as half. Section A, if you see it, this is the stiffener. This is the stiffener here. This is the section A. So this is on the tension side flange. This will cause tension and this will cause the compression on this. So here we can see, according to AISC 360, stiffeners must be provided opposite the tension girder flange if tensile force exceeds the capacity of the column flange. This is the capacity of the column flange. If it exceeds, the tensile force exceeds this capacity, then we need to provide the stiffeners on opposition. And when the loading is applied more than 10 TF from the end of the column, nominal strength of the column flange is given by, this is the one. When the loading is applied more than 10, this is the end of the column, and 10 times thickness of the flange. If this distance is more, 10 TF. And this is 6.25 times thickness of flange square, and the flange means this column flange is the right, that column flange thickness. Whatever the force it's coming here, this is the column flange, right? This is the column. This is the column flange, thickness of column flange, and yield strength of the column flange. Yield strength of the column flange. If the loading length across the column flange is less than 0.15, where B is the column width. If you see this column width, this is the column width. If you consider like this, this is the column. If this column width is BF is, if this is BF and the loading length across the column is less than 0.15, then the design capacity does not require verification. Conversely, if the loading is applied within the 10 TF from the column end, that means from this end, if the load is applied within the 10 TF, they must be reduced by 50%. Rn must be reduced by 50%, not 1 or 2%. It's 50%. Half is coming down. The design and allowable flange strength can be derived from AISC. So this LRFD, it's a 5 factor into Rn. That should be greater than or equal to PRF, and ASD, it will be Rn divided by safety factor. This phi is the resistance factor, gamma is the safety factor. So values of PFP, LRF, ASD designs are available in the AIC manuals. So we can see one example. Consider moment connection where the girder frames into the column. Flange the following parameters: M are 50 kips per feet, and then distance between flanges DM 4 feet, girder depth 24 inch, thickness of flange 0.5 inch, axial force is 10 kips, and flange yield stress is 36 KSI. Calculate the force delivered by the girder flange to the column flange. We know that this is the girder, this is the column, right? So from the girder flange, how much is force is transferred to the column flange, that we are calculating it. That is PR. This is the moment divided by DM, and axial force, whatever is that, divided by 2. So moment is 50 kips feet, and we are converting into units kips in inch, substituting this value 600 by 48 inch, 10 kips by 2. So we are getting the force delivered by the girder flange to the column flange is 17.5 kips. Here we can see the calculate the nominal strength of the column flange. We know nominal strength is 6.25 times thickness of flange square. If you increase the thickness of the flange, then capacity also increase, and yield strength of the flange Fy into flange. So 6.25, 0.5 is the flange thickness, 0.5 inches squared, that is KC. So it becomes 56.25 kips. Check if the tensile force, this tensile force 17.5, this is less than the 56.25. The column flange is adequate under the applied loading. So conclusion is, in this example, force delivered by the girder flange to the column flange is 17.5 kips, which is less than the nominal strength of the column 56.25. Therefore, the design meets the required strength criteria. One more problem we can see, the problem statement. Steel girder frames into the column flange moment connection. The following parameters are girder. Girder moment is 80 kips feet, and distance between the flange is 5 feet. Girder depth 30 inch, and girder flange thickness 0.75. Column flange yield stress, and then axial force also there. This is actually not the girder flange, it's the column flange. It should be, because we need the column flange. So technical discussion, if you see the force transmitted from the girder to the column flange must be calculated to understand the loading conditions at the column. This is critical for ensuring the column can support the loads without failure, right? So we need to first calculate what the force is coming from the girder flange to the column flange. So that we need to first calculate it. That is coming from the moment from the girder divided by depth of the effective depth of the girder, and then PR is axial load in the girder divided by 2, because 2 flanges are there. So we can calculate the force delivered by the girder flange. So here we have to convert the girder moments into kips and inches. After converting that, we are substituting this 960 kips inch by 60 inch, the effective depth, and 15 kips axial force divided by 2. So we are getting the force is 23.5 kips. The force delivered by the girder flange to the column flange is 23.5 kips. Then we will calculate the nominal strength of the column flange. Next, we assess the capacity of the column flange to ensure that it can resist the applied loads. It should be able to resist the applied forces, so we have to consider that. Then the nominal strength must exceed the calculated force from the girder, right? Then only it is a pass. Or a nominal strength of the column flange is that 6.25 times thickness of flange squared F into flange. This we know, this is the thickness of the flange 0.75 inches squared and 50 ksi, so we can calculate the nominal strength of the column flange. So check against the required strength. In this step, we compare the force from the girder to the column flange capacity to determine if the design is safe. We need to determine if the design is safe by comparing the force from the girder to the column flange capacity. So we calculated the force from the girder, then column flange capacity also we compared. We calculated, then we are determining if the design is safe or not by comparing these two. This is essential for structure integrity and safety. PRF we know 23.5, RN is 176.5. So since the applied force is significantly less than the nominal strength of the column flange, so the column flange is adequate to support the loading. Conclusion: in this example, we calculate the force exerted by the girder on the column flange and compare to the flange nominal strength. Then analysis showed that the column flange can safely transmit or support the applied forces. It confirms the design adequacy. This step-by-step approach is crucial in structural engineering to ensure safety and compliance with design standards. We can see the web compression buckling overview. The web compression buckling is a critical failure mode that can occur in structural steel columns when compressive forces are applied at opposing flanges in the same direction. Here you can see compressive forces applied at opposite direction in the same locations. Compressive forces are applied at opposing flanges in the same location. This situation typically arises in the moment connection. This is an example of moment connection. This kind of situation, compressive forces acting in opposite direction in the same location, it can arise in the typically in the moment connections, particularly at the bottom flange of back-to-back girder connections configuration under gravity. Here you can see particularly under the back-to-back, this is one girder, second girder, back-to-back girder at the bottom flange. Bottom flange it will come under compression due to the gravity loads. Because of the gravity loads, the top flange it will try to come like this, and bottom flange it will go towards like this. This will cause the compression for this here this location of the web of this column. Physical explanation: when a compressive load is applied to a column, it can create instability of the web of the column if compressive forces are not adequately resisted. See this compressive force, if it is not adequately resisted by this column web, suppose if stiffness is not there, only this column web is going to take this compressive force. If it is not adequately designed, this column web, it will create instability, right? This instability magnifies as the buckling, which can lead to sudden and catastrophic failure. Buckling will not have any warning, unlike bending. The key parameters influence this behavior include geometry of the column, material properties, and loading conditions. Forces: what are the forces at play? If you see girder moments, you can see the girder moment MR1 and MR2. These girder moments from the right and left girders respectively create a bending effect. It's creating a bending effect which results in compressive force at the bottom flange of the column. Because of these moments, bending effect is created. The bottom flange is under compression, which results in compressive forces at the bottom flange of the column. Distance between the forces. The distance dm between the flange force is crucial. Here, this distance dm, this is important. This is crucial because it affects how the moments distribute along the column and subsequently influences the buckling behavior of the web. If dm is high for the same magnitude, the force it would come less, because force we can calculate moment divided by distance. So if this distance depth is more, then compressive forces it will be less. Then the flange it can resist that force. If the force is more, the flange may be under greatly higher stress, It can lead to the buckling and it can lead to a catastrophic failure. Which can lead to sudden and catastrophic failure. So reinforcement solutions to prevent this web compression buckling. Various reinforcement methods can be employed. One of them is to place this kind of a stiffener also, right? Stiffener plates. These plates can be used individually or in pairs to increase. Here you can see this is the pairs to increase the stiffness of the web and prevent the local buckling. Doubler plates. We can use doubler plates also. Full depth doubler plate can be applied to increase the overall strength and stiffness of the web, making it less susceptible to buckling. Here you can see this web doubler plate. Here you can see this web doubler plate. Like this, we can add up additional 2 web doublers. It can reinforce this web and it can take these compression forces. This is the girder and these are the plug wells, and this is the web doubler. This is the column web. If you take a cross section AA, this is the cross section AA. You can see this is the web, and we are strengthening the web with the web doubler with plug weld, and all around we can put the flat weld also, or we can add some web doubler like this also. Alternative web doubler plate detail. This is detail of web doubler plate. Here we can see this force transfer. The force transmitted from the girder flanges to the column can be calculated as moment divided by dm. This is left moment acting on the right hand girder, mr1. Moment acting on the right hand girder, mr2. Moment acting on the left hand girder. dm is nothing but the distance between the flange forces. dm equal to overall depth minus thickness of the flange. This equation illustrates how the total moments, these moments influences the force exerted on the column web, emphasizing the relationship between the geometry of the assembly and resulting forces. Then we can check the nominal capacity of the column. Nominal capacity Rn of the column web against buckling is given by 24 times TW cube. So if we increase the column web thickness, nominal capacity of the column web against buckling is increasing because it's directly proportional, and square root of E into FYW, web yield strength, divided by height. Height is the clear distance between the column flanges minus corner radius at each flange. FYW is the yield stress of the web. TW is the thickness of the column web. This formula indicates that the strength of the web is heavily dependent on its thickness, TW, strength of the column, heavily dependent on the thickness and yield strength of the material, and increasing the web thickness or using higher grade steel can significantly enhance the buckling resistance. Reduction in capacity. If the load is applied to the column flange at a distance less than d by 2 from the end of the column, the nominal capacity Rn is halved. That means if we have the column like this and the force is applied, this is the column flange, this is the column flange and the column web, this is the column end. From the end of the column, the force is acting at a distance less than d by 2. If it is acting less than d by 2 compressive force, then capacity of the column, nominal capacity Rn is halved. Halved means it's reduced into half, like half the value. Here you can see 0.5 times Rn. The revised Rn is 0.5 times Rn. This reduction accounts for the increased risk of local buckling due to the proximity of the load to the column end. Why are we reducing this capacity? The reason is that this has to account for this reduction accounts for the increased risk of local buckling due to the proximity of the force proximity of the load to the column end, where lateral support is weaker. Available compression strength. The available compression strength of the column web can be determined using AISC specifications. LRFD, load resistance factor design. 5 is the resistance factor, typically 0.9. This ensures that design is conservative and accounts for uncertainties in load assumptions and material properties. There would be uncertainties in material properties as well as load assumptions. So to account for that uncertainties, this method makes a conservative design, like including the 5 resistance factor is considered. An allowable stress design. Gamma is the safety factor that usually reaches 1.67. This provides safety margin to ensure the web can withstand the applied forces. Interpretation. The calculation and principles outlined above emphasize the importance of understanding the interplay between the applied forces and structural stability. There is a interplay between the applied forces and structural stability. If the applied forces are higher, it can cause some increased risk to structural stability. By appropriately reinforcing the column web and ensuring that the design accounts for the potential for buckling, engineers can significantly enhance the safety and reliability of the structural system. The engineer's main duty is to enhance the safety and structural reliability of these systems, right? The choice of materials, geometry, and reinforcement methods must be carefully considered to prevent failures and ensure that the structure can support and anticipate loads over its service life. Here we can see one numerical example. Consider column subject to compressive forces from the two girders at the bottom flanges, and the parameters for the girders given and column are as below. MR1, moment acting at the right hand girder, moment acting at the right flange header, distance between the flanges, girder depth, girder flange thickness, and web thickness of the column, TW, and yield stress of the web of the column, and clear distance with the column flanges such. That is also given. All these are the inputs that's given. So first step is to calculate the force delivered by the girders to the column. So we use the formula PRF equal to MR1 plus MR2 divided by DM. So we know this formula. Convert the moments to consistent units from kip feet to kip inches. Then we have to multiply 12 inch per feet. We are converting feet into inches. Kips feet, we are converting into kips inches. We calculate the total moment and the force also, and we need to calculate the second step is nominal capacity of the column web. We know the formula for the nominal capacity, Rn equal to 24 times TW cube in square root of EFYW by H. So we know the Young's modulus of the steel is 29,000 and TW cube 0.6 per cube. Calculate EFYW, calculate square root of this value, and then now substitute in the formula 24 times 0.216 times 1204 by 24. It becomes 622.46 kips. The next step is check for the load application distance. If the load is applied at a distance less than d by 2 from the column end, that means with the d 36 inch, so d by 2 we know. Assuming the load is indeed applied within this range, then we need to reduce Rn by 50%. Then we can compare the available compression strength. If you see it, LRFT it's a 5 Rn, 5 is 0.9 into 311 is a 280. That is it should be greater than PRF. So check against PRF 280. Our PRF is 41, so it is pass. So same for ASD. So Rn divided by safety factor. Rn is 311. Safety factor 1.6 and becomes 186. So if you check against PRF, it is pass only. So in this example, the web of the column is adequately designed to resist the applied forces. Both LRFT and ASD criteria are satisfied, demonstrating that the design effectively addresses the risk of web column compression buckling. The calculations emphasize the significance of load, geometry, material properties in ensuring structural safety and reliability integrity. So we have 4 questions to ask. What is the web buckling of the column? Web buckling occurs when compressive forces causes the web of the column to lose its stability, leading to lateral deformation. This can significantly reduce the column's load bearing capacity. This you understand, right? Web buckling happens only when the compressive forces acts in play, and that causes the web of the buckling to lose its stability. Buckling means it losing its stability. Because of that, if it loses stability, it's leading to a lateral deformation, right? That can significantly reduce the column's load carrying capacity. If the column is not able to carry the load, then its purpose is defeat, right? So what factors contribute to the web buckling? So what is the web buckling? The next question is, what factors contribute to web buckling? What factors contribute? Factors like include web thickness, columns web thickness. We have seen TW cube, right? And the clear distance between the flanges. We have seen the DM, that is also important because it reduces the forces, the applied load. The load also is important. The yield strength of the web material, FYW, also the presence of any imperfections or eccentric loading. This is a very important factor. So what factors contribute to web buckling means the main point is presence of any imperfections and eccentric loading also. How is the strength of the column assessed? So how do you assess the strength of the column, or how is the strength of the column assessed? We can calculate the nominal capacity of the column. The nominal capacity of the column web is assessed using the formula Rn equal to 24 TW cube E into FYW square 0.5 divided by S, right? TW thickness, Young's modulus, FYW, and considers the clear distance of the flanges. What is the effect of slenderness ratio on the web buckling? What is the effect of slenderness ratio on web buckling? A high slenderness ratio, or ratio of effective length to web thickness, increases the likelihood of buckling. If the slenderness is high, it increases the likelihood of buckling. That means buckling can occur. There are more probability. Slender webs are more prone to instability under compressive webs. So if the webs are slender, they are more prone to instability under compressive loads. Next question is, how can web buckling be prevented? How do you prevent the web buckling, or how can the web buckling be prevented? Prevention can include increasing the web thickness. We know that it's directly proportional to the web thickness. We can increase the web thickness or using stiffeners or double plates. Ensuring proper design connections, avoiding eccentric loading conditions. These are the factors by which we can avoid the buckling of web. How can web buckling be prevented? What role do stiffeners play in preventing the web buckling? What role do stiffeners play in web buckling, preventing web buckling? Stiffeners provide additional support to web, increasing its overall strength and stiffness. They help to distribute the loads more evenly and reduce the effective span of the web, minimizing the risk of buckling. What happens to a column if web buckling occurs? So the question is that what happens if the column web buckling occurs? If web buckling occurs, what happens to the column if web buckling occurs? If web buckling occurs, the column may experience a sudden loss of load carrying capacity. So if it buckles, it means that it experiences a sudden loss of load carrying capacity, leading to potential structural failure. This can happen without visible warning. So this is the important problem. Like without visible warning, it can lose its strength, or it can lose load carrying capacity suddenly, making it particularly dangerous. Are there design codes that specifically address web buckling? Yes, there are design codes that address web buckling. Yes, design codes such as AISC and Euro code provide guidelines and equations for assessing and designing against the web buckling issues. Street structures. How does the load eccentricity affect web buckling? So how does the load eccentricity affect the web buckling? This is an important question. Load eccentricity. We know that load eccentricity increases the likelihood of buckling because it introduces additional bending. If there is an eccentricity, it introduces additional bending moments, right, on the web, exacerbating the compressive stresses and leading to instability. What is the importance of regular inspections in relation to web buckling? What is the importance of regular inspections in relation to web buckling? Regular inspections can identify signs of distress or deformation in the web before buckling occurs. Early detection allows for repairs and reinforcements, enhancing the safety and longevity of the structure.